Okay. So this first definition that we're going to look at is differentiability at a point. Okay. So much like continuity, we looked for continuity at a point. And that's where we would actually write out limit from the left, limit from the right, f of whatever that value was, and show that they were all the same, right? So differentiability is going to be a little bit similar. A lot of times we'll be considering it at a single point, and we will have to prove that that's the case there. Differentiability on an interval is when the function is differentiable on that interval. So a lot like our definition for continuity, a function was continuous on an interval if it wasn't discontinuous anywhere on that interval, right? So much the same, you're differentiable at a point if your derivative exists at that point. You're differentiable over an interval if you are differentiable at every point on that interval there. So this is going to be super duper important. This last thing right here, I would put a star next to it. A function must be continuous in order to be differentiable. Something can be continuous but not differentiable. However, if it's not continuous, it's definitely not differentiable either. Okay? So when you're checking for differentiability, you really want to check continuity first. Then you check differentiability for that. So if we look at this picture here, okay, this is the primary example of differentiability. Okay? Consider the function f of x equals the absolute value of x plus 3. The first part asks us for f prime of negative 5. So that is right here on my graph. Xander, what is f prime of negative 5? It is negative 1. Perfect. That's just the slope of the graph at that point, right? And so the slope of that graph, since it's a straight line, is just negative 1. Then it asks for f prime of 0. Emma, what is f prime of 0? What is f prime anyway? What's the derivative? Slope. So at 0, Emma, what's the slope of that line? It's just 1. Good. All right, so this is pretty easy to find at almost every point on the graph, except where? The next one they ask us for, at negative 3, right here, at this point. Saying what the slope of that graph is not really going to be possible. Because on the left side, what's the slope? Negative 1. But on the right side, what's the slope? Positive 1. And you're looking at the very point where it switches, right? So we would say that this, I forgot to look that up. I think we say it does not exist. Or is it undefined? I can't remember. I'll take either one for right now. I do need to, I'm going to make myself a note. I need to go look that up sometime. F prime of negative 3 D N E or undefined. I'm not sure.
So the short term
Maybe,
make a discontinuity.
yes. Well, there, it makes the function not differentiable at that point, but it is still continuous, right? Because we could trace the whole graph without having to pick up our pencil. So it is still continuous at that point, but it is not differentiable, right? We cannot take the derivative. Functions are not going to be differentiable at any sharp turns. So if you have a sharp turn in the graph, then it's not differentiable at that point where you have the sharp turn. Another word that is sometimes used for a sharp turn is a cusp. So that's cusps. That is an acceptable word to use if you would like, but they'll take sharp turn. If you say this is not differentiable because there's a sharp turn in the graph, they'll take that. But it can also be called a cusp. Alright, so in order for a function to be differentiable at a point x equals a, first of all, f of x must be continuous at x equals a. So, got to be continuous at that point. If it is not continuous, then it is not going to be differentiable. Okay, so you'll always check for that first, then to check for differentiability. Okay, so to check for differentiability, your derivative on the left side has to equal your derivative on the right side. So the limit, I'm going to use limit definition of a derivative. Limit as x approaches a of f of x minus f of a over x minus a from the left has to equal the limit as x approaches a from the right of f of x minus f of a all over x minus a. Okay, you could also use the x plus h definition there to get a expression for f prime of x. So let's write this down, I guess. Or use the what am I doing here? Use limit as h approaches 0 of f of x plus h minus f of x over h to find f prime of x and show limit as x approaches a from the left of f prime of x equals the limit as x approaches a from the right of f prime of x. So either one of those limit definition of a derivative equations can be used, just depending on which one you're more comfortable with or would like to use there. Okay, a function is not going to be differentiable at any place where it's not continuous. So if you have an asymptote or if you have an asymptote or a jump or a hole, then the function is not differentiable at that point. If you have a sharp turn, the function is not differentiable at that point. And then a vertical tangent is also going to be a place where it's not differentiable at that point. Okay? Tyler, you with us?
Somewhat.
All right. Okay. So, here's an example of what you're going to be asked. Most of the time they ask this either about a graph, which is easier, or a piecewise function, which is going to be more work, right? So the first thing you must do if a function is going to be differentiable is first check to see if it's continuous. So we've already done continuity quite a bit, right? So to do continuity, what do we need to do? From both sides, all right? So we would say the limit as x approaches 0. Actually, first of all, this is for all values of x, but what's the only one we really care about? 0. this is just a line. This is just a quadratic. The only one that we're not going to have continuity at is at the point where these two pieces come together, right? So limit as x approaches 0 from the left of f of x is just going to be the limit as x approaches 0 from the left of x plus 1, and that is going to be 0 plus 1, which equals 1. Okay. The limit as x approaches 0 from the right of f of x is going to be the limit as x approaches 0 from the right of x plus 1 squared, which is going to be 0 plus 1 squared, which also equals 1. It's looking pretty good so far. What's that third thing I've got to check? F of 0. I already know it's just 0 plus 1, right? You're just using that top function. You just get 1 again, but you got to write it down. Therefore, f is continuous at x equals 0, and thus continuous everywhere on its domain. So if you get a no right here, if you get that it's not continuous, therefore it's not differentiable, you could stop on that. But this one is continuous, so we need to go further. So we need the derivative from the left and the derivative from the right at this point. I think it is a little bit easier to use the x approaches a equation for this, so that's what I'm going to use, but you could use the other if you want. So, so your derivative from the left. From the left, which equation do we use? Top one. All right, so we're doing the limit as x approaches a of f of x minus f of a over x minus a. You don't necessarily have to write it down, but I find the more times I write it down, the less likely I am to forget it come quiz or test time, so I'm going to write it down every time. And so, in this case, 0 is my a, so I'm doing the limit as x approaches 0 of f of x is just x plus 1 minus what is f of 0? 1 all over x minus 0. So this is going to give me the limit as x approaches 0 of, essentially in the numerator you just have x over x. And what is x over x? If you plug in 0 right now, it will be 0 over 0. If you cancel these, they cancel, but what do they cancel to? 1. So you're just going to get 1 for that. Okay, so the derivative from the left is 1, and then we're going to do the derivative from the right. So that's going to be the limit as x approaches 0 of f of x, which is x plus 1 squared, minus f of 0, and f of 0 is just 1, all over x minus 0. X plus 1 squared is, well, let's keep our limit notation, limit as x approaches 0. That's going to be x squared plus 2x plus 1 minus 1 over x. Okay, what's going to happen here? Does that happen yet? Plus and minus 1 cancel first. Then we can factor out an x. So be sure not to like just cancel an x that you see. You've got to factor out an x. So that will look like this. X approaches 0. I guess I should have a right. Should have a plus right here. I should have had a left right there. All right, and then we'll do color. We'll have x times x plus 2 over x, and so those x's right there cancel, and we can plug in our 0. So we'll just get 0 plus 2, which is 2. So since my derivative from the left is 1 and my derivative from the right is 2, what conclusion am I going to make? Not differentiable. We would say, therefore, f is not differentiable. At x equals 0. So I've got the different pieces that you need in different colors there. The blue part is what we need for continuity. We've done those several times. That was probably our strongest section on the FRQ that you guys had on the back side there. You guys did pretty well with continuity. The green, derivative from the left. The purple is your derivative from the right. And then your last thing is your conclusion. If the green and the purple give you the same number, then yes, it's differentiable. If the green and the purple give you something different, it's not. Okay, questions? Okay, now, this particular one is multiple choice. So you don't necessarily have to show all of the work that I showed on the last problem. Let f be the function defined above. Which of the following statements is true? F is not differentiable because it's not continuous. It's not differentiable because it has a sharp corner. It's not differentiable because it has a vertical tangent. Or it's not differentiable because f is not defined at x equals 5. So let's worry about A and D first. Is f defined at x equals 5? Can I plug in 5? I can, right? And when I do, I would use the bottom equation. There's an or equal to sign. So f is defined at 5. It's not going to be that. For part A, f is not differentiable at x equals 5 because f is not continuous. Now, I would have to, do limit notation if this were a free response question, but it's not. So when I do the limit, I'm really just plugging 5 into the top and bottom, right? In the top, what am I going to get? 2. In the bottom, I'm going to do 2 times 5 minus 4. And that is going to give me 6, which is not 2, right? So is f continuous at 5? No. So right here is our answer for that. It doesn't matter if it has a sharp corner or vertical tangent. It can't really have either one of those things because it's not even continuous. So A is going to be your answer for that. Okay? All right, let's keep going. Which of the following statements is true cannot be used to conclude that f of 0 exists? So, okay, it is going to be A. Why?
Well, f of 0, limit can exist. Like two sides, they can go to the same point, but that doesn't mean the point exists. It could go to a hole or something.
Right. So, at 0, you could have a hole, but yet the limit still exists at that point, right? So, here's the reason that A may not prove that f of 0 exists. If f is continuous, f of 0 has to exist, right? Can't have a hole where it's continuous. What about c? If it's differentiable, it has to be continuous, right? So you could, like, if c proves that f of 0 exists, then if b proves that f of 0 exists, c has to as well, because you have to be continuous to be differentiable. So it's not an answer. What about this? The graph of f has a y-intercept. Okay, and where do we cross the y-axis? At 0, right? So if you have a y-intercept, that means you cross the y-axis, and the coordinates of that point are 0 some number. So you have a point there. That would only apply for f of 0. If they were asking you about f of 1, then D would not prove anything. But for f of 0, that does mean that this has to exist. Okay? All right, we got one more. And this one is a free response question, and I need to make this, I know you cannot like see that at all right there. I'm going to make this as big as possible. In this case, this is an example of something that you will see fairly often. At an excavation site, the amount of dirt that has been removed in cubic meters is modeled by the function f defined above, where g is a differentiable function, and t is measured in hours. Values of g of t at selected values of t are given in the table above. According to the model, what is the average rate of change of the amount of dirt removed over the time interval from 6 to 12? So if I want average rate of change from 6 to 12 hours, what am I looking for? Just slope between those 2 points. So we would use the points 6, 306, and 12, 474. And we'll just do slope formula. So we'll have 474 minus 306 over 12 minus 6. And gracious, that's going to give me, let's see, 168. Is that right? Over 6. And I know for sure that will reduce, but does it give you a whole number? Yeah, you get 28. This question has units, so we want to include units with our answers. What would our units be? 28 what? Cubic meters. So meters cubed per hour. Because it's your change in y, which is cubic meters, per hour, over your change in x, which is hours. So cubic meters per hour.
You write it out. That's just
Write out cubic meters. Yeah, that's fine.
Okay.
Yeah, that's fine.
I could not write what she just read.
Okay? Questions? Alright, so let's go to the next part. Use the data in the table to approximate f prime of 9, the instantaneous rate of change of the amount of dirt removed, in cubic meters per hour at time t equals 9 hours. Show the computations that lead to your answer. So they want us to approximate f prime of 9. What should we do in this case? Okay, so 9 falls right here between 8 and 10. Right there's our 9. We want to use the two closest points. We're just going to do slope formula again for this one. So in this case, we've got 8, 376, and 10, 428. So we'll have 428 minus 376 over 10 minus 8. And 428 minus 376 is going to be 52 over 2, which is 26. Units are still the same. It's cubic meters per hour.
So it's like what we did on the board, not for that last one, yeah, that's.
Yes. Yeah. You're just going to use those 2 points that are the closest. Okay. For part C, they ask us if f of t is continuous from 0 to 12. So from 0 to 6, we've got like a cubic function here, right? Something to the third power. That is continuous everywhere, right? There should be no problems from 0 to 6 about this being continuous. G, they just gave us a table, so we don't really know, except for they told us G is a differentiable function. So if G is differentiable, what do we know about G? It's got to be continuous, right? Now we cannot just assume that the grader knows we know that. We have to say it. And that leaves just one point where we're not sure, right? That one point is at 6, the 2 places where they come together. So I would say F is continuous on 0, 6 because it is cubic. Oh, don't say it, because F is cubic on that interval. F is continuous on 6 to 12 because from 6 to 12, F is really just G, right? Because G is differentiable and thus also continuous. Alright, so that tells us F is continuous everywhere except for at 6, right? So now we want to say F of 6 equals, and F of 6 up here, which one should we use, the top function or the bottom function for 6? Bottom, and the bottom is just G. What is G of 6? 306. So F of 6 equals, I'm going to even write this. I'm going to write G of 6, which equals 3 over 6. That lets the grader know you know that you're using the table there. If I do the limit as x approaches 6 from the left of f of x, that would just be plugging 6 into the top equation, which I'm going to say this has got to be calculator active, I would think. We're going to do it calculator active anyway. 48 times 6 plus 6 squared minus 6 to the third divided by 12. And I got 306. Did you guys, anybody else try it? Did you get 306? The limit as x approaches 6 from the right of f of x is definitely 306 because it's just read off of the table. Therefore, f is continuous at x equals 6 and therefore continuous on 0 less than or equal to t less than or equal to 12. I might should have used a bracket right there and a bracket here with 12 also. All right, and the last part, let me think about this. I mean, I know how to do this. I'm just trying to decide if I want to have you do this.
I don't think you do.
Let's use a calculator. I'll show you how to use a calculator on this. Alright, everybody grab your calculator. Because we are going to learn the shortcut tomorrow. You could do limit definition of a derivative. Right, when they ask for f prime of 2, you could do limit definition of a derivative. We're getting ready to come to a point in our calculus careers where we do not use limit definition of a derivative hardly ever. So I'm going to show you how to do it on your calculator today. And then tomorrow we're going to look at the shortcut. So, in your calculator, first thing we want to do is go to y equals and put, we're looking for f prime of 2. So which part of the function do we care about? The top or the bottom? Just the top, right? So I'm going to put just the top equation into y1. And I'm going to use x's, excuse me, instead of t's. Well, let's see if it is batteries or if it is try these and see if that fixes it. But it's going to be because it looks like you have mismatched batteries that were probably that bad. Oh no. I hope that it did not put it in the calculator because sometimes that will. Alright, everybody got their function into y1? Everybody's checking their batteries now to see if they're also corroded.
I wanted to know if they were all the same.
Yeah.
I've never heard of a battery called Thunderbolt Edge. That sounds so wrong.
Some of you may have mismatched batteries because I put batteries back in these calculators last, and it was the bottom of the barrel there. All right. If you ever do notice your batteries are like looking sort of corroded, even if it's still working, take them out and let me know. I'll give you some new batteries. You're okay. Let's get you some. Okay. Yeah, if yours are looking a little corroded, it's better to go ahead and replace those because Okay. All right. Go back to your home screen. So just hit that home button. And so if you press F3, it's the tab that says Calc. So if you hit F3, the very first button you have there is differentiate. And so there are two ways that you can do this. The first way is this calculator will take the derivative for you. So that all that limit definition of a derivative stuff we've been doing, it will do all of that for you. So all you got to tell it is y1 of x. That's telling it the equation that you had in your calculator. And then you're going to put comma x to tell it what variable you are differentiating, which is x. And then you'll close the parentheses and hit enter. So let me write it bigger up here because I know it's a little hard to see that calculator and I can't make it any bigger. So you're writing, whenever you hit that derivative button, it'll pull up a d over dx. Actually, on the screen it just puts it d. And then you'll have y1 parentheses x close parentheses comma x. There's no special button for y1. You just type a y and a 1. Now, that will give you the derivative, and you can plug the number in. But there is an even easier way to do it for this particular problem. Did I type it in wrong? Let's see.
No. I did the same thing you did.
When you go to your y equals, does yours look like mine?
Wait, to the third. Is it to the third?
It is to the third, yes.
I can't read that.
Yeah, sorry, it's a tiny copy. It is to the third power. That's probably the difference. There. Okay? So what we could do is we could now just plug 2 into this equation that we're given. But the calculator will even do that for us. So if, like, it should just put that derivative you just typed in into the next line when you hit enter, it's there. This button right here next to your 7, it looks like just a straight line. Okay, this is your such that key. So you're going to hit that. It's going to put that straight line. Yeah, it needs that derivative stuff in front of it, which you could just get from the line above it. So you got that line, such that, and then just type x equals 2. And so when you hit enter this time, it is going to plug in 2 for you. And the answer is 51. And so if this were calculator active, it probably would not be on this piece probably would not be calculator active on a real one. But you're also going to learn a shortcut tomorrow that will make it much easier. All you would have to write would be f prime of 2 equals 51. The line is right next to your 7. It's that button right there. Okay, check on your neighbor, see if they're getting it to work.
I'm sorry.